Current and Ohm's law are going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now this is the first lesson in a new chapter on current and resistance. And we're definitely going to focus on current and Ohm's law, but we'll also talk about the power dissipated across resistors. We'll also talk about resistivity, as well as the temperature dependence of resistance. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now we're going to start this lesson off by defining electrical current. And it's going to be a mathematical definition, but before we get there, just think about where you might use the word current in your everyday life. And it's probably going to involve like wind currents or ocean currents or river currents, but it's probably going to involve the flow of either air or water. Well, with electrical current, we're talking about the flow of charge. And we give it this mathematical definition. We use the capital I to represent electrical current, and it is the change in charge over the change in time, or the flow of charge over time, if you will. So let's say you had a circuit and you had a gate on a wire in the circuit, and as charge was flowing by that gate, so you had some way of counting the charge as it went by. That's effectively what current is. It's a measure of that change in charge or flow of charge per unit of time. The SI unit we call the ampere, or the amp for short, so symbolized with a capital A. And if we look at what that reduces down to, so the SI unit for charge is the coulomb, the SI unit for time is the second, and so 1 ampere equals 1 coulomb per second. All right, now a couple things you should know. So we talk about it as generically the flow of charge, but if we're talking about the flow of charge in a conducting wire, well, really it's the flow of electrons going around that wire. But as we talked about in the last chapter, if electrons are flowing this way, so versus some sort of positively charged species flowing the opposite way, you get the same result. And so in the early days, a couple hundred years ago, all they knew was the result, and they didn't know if it was the flow of positive charges in one direction or negative charge in the other direction, and they chose it backwards. They just talked about it being the flow of positive charges. Now, in certain solutions, you might get the flow of ions, and it could be both positive and negative ions flowing, so it's not completely wrong to say that we could have the flow of positive charges in one sense, but in a conducting material, the protons are confined to the nucleus. It is the loosely held electrons that are actually flowing through the wire. And so actual current is the flow of electrons, but for historical reasons, we define what's called conventional current, which is kind of like the imaginary flow of positive charges, as long as you're talking about a conducting wire, which is pretty much the most common context that'll be brought up in this course. So keep in mind, when we talk about conventional current and current in general, unless specified, it's usually we're talking about conventional current. It is the imaginary flow of positive charges. Just keep in mind that real current is really the flow of electrons in the opposite direction. So now we're going to transition to talking about one of the most important laws in all of second semester physics. It's a rather simple one here, this mathematical expression, but delta V equals IR. Your potential difference equals your electrical current times your resistance in a resistor. So a resistor resists the flow of charge. It resists the current in a circuit, hence the name. We can better see that if we rearrange this a little bit, but also Ohm rearranged this to provide a definition for resistance. And so resistance R is equal to the ratio of the potential difference over the electrical current. And he called the SI unit for resistance the ohm, which we symbolize with the Greek capital omega. Now, if we rearrange this and solve for current, we can get a better idea of why we call it resistance. So current's going to equal delta V over R, and we can see that your electrical current is directly proportional to your potential difference across a resistor. You double that potential difference, you also double the current, but it's inversely proportional to the resistance. If you double the resistance, you would cut the current in half. And so the greater the resistance, the lower the electrical current. The resistor is functioning to lower the current. It's resisting the flow of charge, again, and hence the name. All right, now a resistor, in some cases we actually just have resistors manufactured as structural elements to put inside circuits to function as resistors. But much of the time we're talking about many of your electrical appliances actually functioning as resistors, like light bulbs and toasters. Those are just resistors. And their job is to turn electrical energy into some other usable form of energy. Like in the case of a light bulb, it's turning electrical energy into heat and light. Now the goal is the light. The heat just kind of comes along for the ride. And the greater the amount of light per unit of heat, the more efficient we say that light bulb would become. And LEDs do a great job, incandescent light bulbs not so great. But they dissipate power in this case. They give off energy per unit of time. And that's one of the functions of a resistor, is to give off this power. Now we can talk about this power dissipated in a resistor as well. And that power, it turns out, is equal to the potential difference times the current. So a simple relationship, if you know these two properties across a resistor, you can get the power being dissipated very quickly. And it will come out with units of watts or joules per second. And so a volt ampere must equal a joule per second. Again, the same thing as a watt, and indeed it does. Now, a couple other ways you might see this expressed is we can use Ohm's law and substitute it right in here and get two other equivalent expressions for the power dissipated in a resistor as well. If we just take Ohm's law directly and then substitute in for delta V, I times R, well, you get I times R times I, which overall simplifies down to I squared times R, and that's another equivalent way of getting the power dissipated in a resistor. Instead, if you actually took and substituted delta V over R in for I right here, you'd have delta V times delta V over R, which would give you delta V squared over R. So three different ways to calculate the power being dissipated in a resistor. Now, one thing you need to know, it's the power being dissipated in a resistor, and that's going to involve the potential drop just across that resistor. Now, if you only have one resistor in a circuit, typically the EMF of the power source is going to be the potential drop across the resistor. They'd be one and the same. But if you got more complex circuits that have many resistors, that's typically not going to be the case. And the rookie mistake some students will make is they'll just look at, their circuit diagram and they'll see the EMF source and it'll say 12 volts. And no matter what calculation they're doing on the problem, they're going to plug in 12 volts every time they see delta V. And that's where you got to be careful. It's just the delta V off the resistor of interest in a problem, not necessarily the same thing as the delta V of the EMF source in most cases. So you got to be careful. So I personally like this middle definition because it's impossible to make that rookie mistake. But again, technically any one of these three should give you the power dissipated across a resistor. And let's jump into doing a little bit of plugging and chugging. So first question here says a current of 3.0 amps flows through a 2.0 ohm resistor. What is the potential drop across the resistor? First question. What is the power dissipated across the resistor? Second question. All right, so the potential drop here is just straight up Ohm's law. Delta V equals I times R. And in this case, it's given. So I is 3.0 amps. R is given as 2.0 ohms. And 3 times 2. Delta V is going to be 6.0 volts. That is the potential drop across the resistor. So typically, when you convert electrical energy into some other form of energy, the amount of potential energy stored in the charge that's flowing is going to go down. And again, if we're envisioning the imaginary flow of positive charges here, so potential energy of those positive charges goes down as potential goes down. And so typically we're going to associate delta V as a potential drop. Now we're just going to put an absolute value of 6 volts here in this case, but in more complex problems, we really will reflect it as a drop of 6.0 volts in the future. All right, the second part of the question was, what is the power dissipated across the resistor? And we've got 3 different equations we could use now that we know delta V here. And we know all 3. We could actually use any one of these 3, but I like the one that doesn't involve squaring anything because it usually involves lower numbers. And that's what I'm going to use here. So delta V times I, which in this case is that 6.0 volts, times our 3.0 amps. And that is a power being dissipated of 18 joules per second, or watts. And you can see how the other 2 formulas would have led us to the same place. So I squared times R would have been 3 squared, which is 9, times a resistance of 2 ohms would have got us 18 watts. Or delta V squared over R would have been 6 squared, or 36. All over R of 2 would give us 18 watts as well. So again, any one of these 3 should work. If they don't all 3 give you the same calculation, you might be making that rookie mistake. Next, we want to talk about what is known as the resistivity, and it's related to the resistance for a substance. And it's indicative of some conducting substance, typically is the context it's brought up in. But before we get there, I just want to kind of allude to a simple circuit for a minute. so we don't get kind of confused of, we're going to talk about resistivity and then we're largely going to ignore it for much of the next two chapters. So if we take a look at a simple circuit here, so we talked about in the last chapter that two parallel lines with one's short and one's long, that is a battery or a source of EMF. And then this jagged line right here, that is the symbol for a resistor. And so in this simple circuit, we have one source of EMF and we have one source of resistance, or so we think. Now it turns out your load resistor is usually the greatest contributor to resistance in a circuit. But we'll find out that batteries themselves often have, or typically have, an internal resistance that we usually ignore. But also the wires themselves that are made of a conducting material typically have some sort of resistance associated with them as well, depending on what material they're made out of, but also depending on kind of their design. So how fat is the wire and how long is the wire, as we'll see in just a second. But we usually ignore that as well. And so usually on a simple circuit diagram like this, we ignore the fact that the battery has any internal resistance, we ignore the fact that the wires themselves have resistance, which we're about to talk about, and we pretend that the only source of resistance is the resistors that appear in the diagram. So just keep that in mind. All right, so resistivity here is talking about the resistance in the wires typically. So, and it turns out it totally depends, the resistance of a wire, let's say, depends on how long the wire is. And it turns out the longer the wire, the greater the resistance. But it also depends on the cross-sectional area of the wire as well. The larger the cross-sectional area, the smaller the resistance to the flow of charge. And you kind of think of this analogous as kind of water flowing through a hose. Now, if you've ever had to siphon gas, and maybe you have, and hopefully for completely legal reasons, you've had to siphon some gas. So a couple things I recommend: use a short hose. So if you use a long hose, you're going to get greater resistance, and it's going to be harder to get that gas flowing from out of the gas tank in most cases to the other end of that hose. So if I used a hose that was 1 mile long, I put the hose in a gas tank and I went to the other end 1 mile away and I start sucking on it, you're not getting any gas out of that thing. There's just not going to happen. So because it's going to have such great resistance to the flow of water, and in the same way, the longer a wire, the greater the resistance to the flow of electrical current as well. Now it turns out resistance is going to be inversely proportional to the cross-sectional area. Now the other thing I would recommend doing if you're siphoning gas is to use a pretty good size hose. If you use like the really thin IV hose like you might find in the hospital hooked up to an IV, it's really thin and narrow. And so instead of using a short hose, use a long one, but now you use a really thin one, you're just sucking on that thing all day long, and it's going to be tough to get the gas flowing in that one as well. You want to use a much larger cross-sectional area hose because it's going to have lower resistance when it has a larger cross-sectional area, and you're more likely to get gas flowing through it, so to speak. Same thing here, a larger cross-sectional area for a wire, and you're going to have less resistance and greater current flowing through that wire. All right, and then the Greek letter lowercase rho here, that is the resistivity. And that is the part that is going to be characteristic of that particular conducting material. And you can look up these resistivities for all sorts of materials, typically like conducting metals and stuff like this. And you can see which metals are more conductive than others as a measure of that resistivity. Now again, the shape and length of that wire is going to matter, but you've got to get an idea of, well, if I want the most conductivity, which conducting material should I use in principle and things of that sort. All right, now we'll find out also that this resistivity also has some temperature dependence as well, but typically the values that you're going to find reported are going to be kind of reported at some standard temperature like 20 degrees Celsius or something like this. Now you might be involved in doing some simple plug and chugging with this equation for resistance and resistivity, or you might just simply have to understand the relationships. Now one thing to note, since resistance and current are inversely proportional, then any relationship you establish between resistance and any one of these three, it would be the opposite relationship with current. So here I can see that resistance is directly proportional to resistivity. Well, then the electrical current would be inversely proportional to the resistivity. Resistance is directly proportional to the length of the wire. Current would be inversely proportional to the length of the wire. So resistance is inversely proportional to the cross-sectional area of the wire. Your electrical current would be directly proportional to the cross-sectional area of the wire. So kind of works that way. So next question here, we'll do some plugging and chugging. A piece of copper wire has a resistance of 8.00 ohms. It is replaced with a new piece of copper wire that is 3 times longer and has a radius that is double the original. What is the resistance of the new wire? So a couple things we want to look at here. So we want to look at that relationship between resistance and the length, and they're directly proportional. and then resistance in the cross-sectional area, and they're inversely proportional. And in this case, the original wire was 8 ohms for resistance. The new piece of copper wire is 3 times longer. So, and if we've got a wire that is 3 times longer, then that's going to increase the resistance by a factor of 3 as well. Now, we're also told that the radius of the wire is doubled. Well, we see cross-sectional area, we don't see radius, so don't just double it here. So cross-sectional area, typically a wire has a round cross-sectional area, it's a circle, and that area is pi r squared. And so in this case, if you double that radius, that's going to quadruple the cross-sectional area. And if we quadruple that cross-sectional area, that's going to cut the resistance by a factor of 4. It's going to be a fourth of the value. All right, so we can see that with what we did to the length, we tripled the resistance. With what we did to the radius and therefore cross-sectional area, we reduced the resistance by a factor of 4. So in this case, overall, sum these two up, and it's going to be times 3 and times 1/4. And so the resistance is now going to be 3/4 of its original value. Well, the original value was given as 8.00 ohms, and 3/4 times 8.00 ohms, probably do in your head, is now 6.00 ohms. Now we want to briefly talk about the temperature dependence of the resistivity for a substance. Turns out that for conductors, they tend to be more conductive at lower temperatures, less conductive at higher temperatures. And while it's the opposite for semiconductors, we're going to kind of exclusively talk about conductors in this course. And one of the reflections that they are more conductive at lower temperatures is they have a lower resistivity at lower temperatures, as we'll be able to see in this equation a little bit. But ultimately, if you know the resistivity at one temperature, and it might be a value you looked up in a table online somewhere or something like that, but then you can calculate the resistivity at a second temperature, provided you know what's called the temperature coefficient of the resistivity for that substance. And from there, it'll be plug and chug. Now, one thing to note, delta T here. In chemistry, we like to think of that, involving like a process that's undergoing a temperature change, and it's T final minus T initial. Well, we're not doing a temperature change here. We're just comparing two different temperatures. But the final, you kind of think of it as the temperature corresponding to the new value of the resistivity you're trying to calculate, and the initial temperature as being the temperature corresponding to the value of the resistivity you already know. So some textbooks define this with like rho 2 and rho 1, which would be then T2 minus T1, same diff, but this is kind of the convention I'm going with. All right, now one thing to note, resistance and resistivity are directly proportional, and because they are, there's a directly analogous equation that compares the resistance of a wire, let's say, at some new temperature compared to a value you already know at some other temperature. But it's directly analogous, so R equals R naught times 1 plus alpha delta T. And the idea goes like this. Let's say you raise the temperature on a conducting metal and the resistivity goes up by 5%. Well, if the resistivity goes up by 5%, then the resistance will as well, since they're directly proportional, which is why the equation works out exactly the same. All right, let's do a calculation here. The question says, a piece of copper wire has a resistance of 8.00 ohms at 20.0 degrees Celsius. What would its resistance be at 50.0 degrees Celsius? And then the temperature dependence the temperature coefficient of resistivity is given in parentheses as 0.00393 per degree Celsius. From here, we can do some plugging and chugging. So we'll use the second of these two equations to get the resistance directly. So we want to solve for that resistance at some new temperature, 50 degrees Celsius. The resistance we know is 8.00 ohms. I'll multiply that by 1 plus, and that temperature coefficient is given as 0.00393 per degree Celsius. And multiply that by the temperature change, T minus T naught, which is going to be 50.0 degrees Celsius minus 20.0 degrees Celsius. Cool, and make sure you get your parentheses right here, so we get a couple different sets of them. One thing we should note is that because we're looking at a second temperature that is now higher, we should expect a higher resistance corresponding to that lower conductivity for a conductor at a higher temperature. Let our calculator do the heavy lifting for us. So 8 times parentheses 1 plus 0.00393 times 30, and I'll close my parentheses. And we're going to get 8.9432, which in this case I want 3 sig figs, so 8.94 ohms. And that matches expectations that at a higher temperature, 50 degrees Celsius compared to 20 degrees Celsius, that the resistance should go up. Now I want to conclude this lesson by just briefly talking about superconductors. No math, no calculations, just a conceptual understanding of what they are. And the big key is this: you need to understand that a superconducting material has effectively a zero resistance associated with it. And the reason it has zero resistance is because it has a resistivity of zero as well. Now the problem is that superconducting materials that we know of, they're not always superconducting. They're only superconducting as you lower the temperature below some certain threshold temperature. And unfortunately, for every superconducting material we know of, those threshold temperatures are really, really, really low, way lower than kind of any normal outside temperature you're likely to experience, even in cold climates. And so having a superconducting material that operates in anything resembling ambient temperature anywhere on Earth is not the most likely thing just yet, but we're doing quite a bit of active research. And it's kind of a big deal if we could find one that operated at something resembling more ambient temperatures. If you think of like your power lines, so there's a lot of energy dissipated just in the transmission of electricity along those power lines. So your power lines might stretch for miles sometimes in length. And that great length corresponds to a great resistance. And that great resistance corresponds not only to a great potential drop, but a great power being dissipated across those power lines as well. And so real increase in efficiency would be possible if we could replace all those power lines with superconducting power lines. Not presently possible, but maybe, just maybe, in the future. If you found this lesson helpful, consider giving it a like. Happy studying.